Today we are going to see another examples of efficient estimators. So now we have x1, x2, xn from uniform 0 theta, and we have to check efficiency of x bar with respect to x ordered n into n plus 1 upon n. So as we know that sample mean is unbiased estimator of population mean. Estimator of population mean. So expected value of x bar is equal to mu, and we know that variance of x bar, variance of summation xi upon n, 1 upon n square into variance of summation xi, 1 upon n square into summation of variance of xi, and which comes out to be sigma square upon n. Variance of xi is a sigma square, n times sigma square upon n square, sigma square upon n. So we have, now we have to check whether x ordered n into n plus 1 upon n is unbiased and its variance. So now consider let y is equal to x ordered n. So we have to find the distribution of x ordered n, sampling distribution of x ordered n. Consider its distribution function fy. It comes out to be probability that y less than or equal to y, probability that x ordered n is less than or equal to y. But we know that xn, x ordered n, is maximum of x1, x2, xn is less than or equal to y. So as maximum is less than or equal to y, so all observations will be less than or equal to y. So x1 less than or equal to y, x2 less than or equal to y, xn less than or equal to y. So as x1, x2, xn are independent, they are random sample, so from uniform 0 theta, so we take their multiplication. Joint distribution can be written as product of their margins since they are independent. So x1 less than or equal to y, but xi follows uniform 0 theta. So fxi will be xi minus xi fx will be x minus a upon b minus a, that is x minus 0 divided by theta minus 0, which comes out to be xi upon theta, x by theta. So we have this. So x1 less than or equal to y is y by theta, xn less than or equal to y is y by theta. So y by theta raised to n is a distribution function of x ordered n. So now we have to find its probability distribution, fy. Fy is d by dy of capital Fy. We have to differentiate this distribution function with respect to y. So n y n minus 1 divided by theta raised to n. Since all x1, x2, xn lies between 0 to theta, so their maximum will be always lies between 0 to theta. So here range of y will be 0 less than or equal to y less than or equal to theta. So fy is a distribution function and it is given by, now we will find expected value of y. Expected value of y is integration 0 to theta y fy dy, but here fy is n y raised to n minus 1 upon theta raised to n dy. So upon theta raised to n is a constant. Take outside the integration. Integration 0 to theta y raised to n. So n upon theta raised to n, y raised to n plus 1 upon n plus 1. We have to put the values of y 0 to theta, which comes up to be n upon theta raised to n. And by putting theta in place of y, we have theta raised to n plus 1 upon n plus 1. And by taking 0, it 0. So n upon n plus 1 into theta is expected value of y. So expected value of y, n upon n plus 1, expected value of y is nothing but expected value of x ordered n, which is equal to n upon n plus 1 into theta. So we have to multiply this by n upon n plus 1 into expected value of x ordered n is equal to theta. So it comes in the expectation since it is constant. So expected value of n plus 1 upon n into x ordered n is equal to theta. So which is our estimator. Now we have to find the expected value. Now we have to find the variance. So find variance. We have to calculate expected value of y square. Expected value of y square is integration 0 to theta y square fy dy and y raised to n minus 1 upon theta raised to n dy. So n upon theta raised to n is constant. Take outside the integration 0 to theta y raised to n plus 1 upon y raised to n plus 1 dy. So here 2 minus 1 is plus 1. So we have n upon theta raised to n, y raised to n plus 2 divided by n plus 2, 0 to theta, which comes out to be n upon theta raised to n, theta raised to n plus 2 divided by n plus 2. So which comes out to be n upon n plus 2 theta square. And we know that variance of y is expected value of y square minus expected value of y bracket square. But what we have? Expected value of y square, n upon n plus 2 into theta square minus n upon n plus 1 theta raised to 2. Since expected value of y is n upon n plus 1 into theta. Now we have to simplify this equation. And what we have, we can take theta square and n square outside the theta square outside the common. We can take it as common. So what we have, n upon n plus 2 minus n square upon n plus 1 bracket square. Now we have to simplify this. So variance of y, theta square, now we take LCM. So n into n plus 1 bracket square minus n square into n plus 2 divided by n plus 2 into n plus 1 bracket square. So theta square into n square plus 2n plus 1 minus n cube minus 2n square divided by n plus 2 n plus 1 bracket square. So theta square into n cube plus 2n square plus n minus n cube minus 2n square divided by n plus 2 n plus 1 bracket square. So n cube get cancelled, 2n square get cancelled. So n into theta square divided by n plus 2 into n plus 1 bracket square. So this is a variance of y. Now we have to calculate variance of n plus 1 upon n into x ordered n. So n plus 1 upon n square into variance of x ordered n. So n plus 1 square divided by n square into variance of x ordered n is a variance of y. So n theta square divided by n plus 2 n plus 1 bracket square. So n plus 1 square get cancelled, n get cancelled. Theta square divided by n into n plus 2. This is a variance of our estimator. So now we have to go for calculating variance of x bar. Variance of x bar is a summation variance of summation xi upon n, 1 upon n square into summation of variance of xi, 1 upon n square into variance of xi is b minus a bracket square divided by 12. So here b is uniform 0 theta, so theta square by 12. So theta square by 12, this is n times. So theta square upon 12n. This n get cancelled. Now we will find efficiency of x bar with respect to other estimator x ordered n. So now we calculate variance of n plus 1 upon n into x ordered n divided by variance of x bar. So what we have, theta square divided by n into n plus 1 by 2 divided by theta square by 12n. So theta square get cancelled. 12n divided by n into n plus 2. So 12 divided by n plus 2. X to xn belongs to, or take random sample from normal inverse sigma square, and we have to show that sample mean x bar and sample median MD both are unbiased estimator of mu. Both are unbiased estimators of mu. So now we will see. As we know that sample mean is unbiased estimator of population mean, so expected value of x bar is equal to mu, and variance of x bar is equal to sigma square upon n. Now we know that expected value of median is also mu. So mu is unbiased estimator of so median is an unbiased estimator of mu, and we know that sampling distribution of median for large sample, for large n, sampling distribution of median for large n, that is n tends to infinity, the distribution of median for large n is approximately normal, and it is given by distribution function, or it is simply a distribution of median for large n is proportional to exponential of minus 2n f1 square into x minus mu bracket square dx, where f1 is median ordinate. Median ordinate, that is it is equal to, that is a value of fx at x is equal to mu. that is value of fx at x is equal to mu, and which is given by 1 upon sigma root 2 pi. This is a f1. So now we can write this function as the distribution of mean deviation median is given by exponential of minus half into 1 upon 4n f1 square into x minus mu bracket square dx into x minus mu bracket square into dx. So here it is 1 upon 4. Here it is 1 upon 4. So 2 by 4 is 1 by 2, and we have this 1 upon 4n f1 n square fn1 square. So it is actually 1 upon 4n f1 square. So it is 2 by 4, and this comes out to be 1. So likewise we can write this. So what we have? So variance, it is like minus half x minus mu bracket square divided by sigma square, and this looks like a normal, and this is for n tends to infinity. For large sample it is a normal. So expected variance of MB is variance of median is 1 upon 4n f1 square, 1 upon 4n f1 square, and f1 we know that 4n f1 is 1 upon sigma root 2 pi bracket square. So sigma square into 2 pi divided by 4n, which is equal to sigma square pi by 2n. So what we have, sigma square pi upon 2n is variance of median. Now variance of x bar is sigma square upon n, and variance of median is pi into sigma square upon 2n. So variance of x bar is less than or equal to variance of MD. So x bar is efficient than median. So this is the last example on efficiency. Thank you.